So now in this session we'll go for the next part, the second part of the second experiment, that is narrow band stop filter. Okay, so let me show the right up part of that. So narrow band stop filter. So this is a circuit, a 2T network that we are going to use over here. The same circuit has been simulated. Okay. So I want to design a narrow band stop filter with a 60 Hz kind of a signal. Okay, I don't want any 60 Hz signal to be passed through my circuit. Okay, it's my aim, my intent. So let me see my simulated circuit. So this is how is my simulated circuit now. So I would like to rebuild onto this multi-sim platform. So I'll double click on multi-sim. Okay. So if I see my circuit, I can easily identify that the components required for my simulation are an op-amp, the biasing voltage, RC, a function generator, and an oscilloscope. Okay, so I'll go to place, click on component. So I'll take the 741 op-amp, I'll place it over here, and then next I'll go to sources. I'll use this VCC, and I'll use a VEE, a negative biasing voltage. I'll use a ground. Okay, and then I'll just go to sources. I'll click on basic. I'll select a resistor and place it on the canvas. Similarly, I'll use a capacitor and I shall place the same on canvas. Okay, then I do require a function generator and an oscilloscope. So function generator and an oscilloscope. Okay, so I have collected all the components required for my simulation now. So I'll just arrange it as per my requirement. I'll just flip it. Okay, vertical. Right click on the component, say flip vertical, so that will get inverting terminal on top. Okay, I'll have this function generator input component. Okay, on the input side. So oscilloscope and output component onto the output side. So this is a biasing voltage, so it's a positive. So I'll just rotate it and place it near to my pin number 7. Okay, and later I'll just place this negative biasing voltage. Okay, negative biasing voltage here, pin number 4. Then this is my ground terminal. Okay, so this is my resistance. I've just moved it out. Okay, so that I can access my R, C, and the ground terminal appropriately. Okay, so if you refer to my circuit, so as I said, it's a 2T circuit. So I'm having 2 resistors, then again 2 capacitors, and a resistor and the capacitor in shunt. Okay, so in order to build the same, I'll use this resistance, place it over here. So I'll just take it one level top, copy it, place my second resistance. Okay, then I'll have 2 capacitors. Okay, then I'll be having 1 resistance which is placed vertical. Okay, and I will be also having 1 more capacitance. Okay, this is also placed vertical. Okay, now I can make the interconnections to the circuit. Okay, and I can connect this terminal over here to form the T network. Of course, it's a 2T network. Okay, then once this structure is formed. Now I can connect a resistance over here, the capacitance to the junction of R. Okay, so I'll be connecting this R to a junction of C. Okay, as we noticed here, R is connected to the junction of C and C is connected to the junction of R. C is connected to the junction of R. Okay, I'll just place it appropriate. Okay, then I'll just connect these two terminals. Okay, and place a ground at it. Okay, then later so once this T network is formed, now I need to give input at this terminal and I need to ground the other terminal. I need to ground the other terminal. So my input is ready. Then the inverting terminal, so if I see to my circuit, so the input has to be applied to this non-inverting. Okay, so I need to connect this non-inverting terminal to this 2T network. So it is a simple voltage follower, so output has to be connected to inverting terminal of the input. Output has to be connected to the inverting terminal of the input. Okay, so this is inverting terminal of input. Okay, this is the connection. I need to give the negative biasing voltage as well as a positive biasing voltage. Okay, and I want to see or I want to interconnect my measuring instrument oscilloscope such that I can witness the band stop operation. So I can just short the two terminals of the ground and connect those two terminals onto a common ground. Okay, and let me say that channel A I am going to connect it to my output and channel B I am going to connect it to my input. Okay, now I have to fine tune the circuit as per my design. So if I see the circuit, this is 39K and this is 0.068 microfarad. Okay, so this is 39K. Okay, even this is 39K and this is 0.068 microfarad. Okay, then these two values, so it is 19.5K and 0.136 microfarad. 19.5K and this is 0.136 microfarad. Okay, I'll just place label on this side. Okay, 0.136 microfarad. Just have connected load resistance. Okay, the same can be done now. I can have a load resistance over here. The other terminal of that has to be grounded. So I'll place a ground. Okay, so one end of this load resistance will be grounded, another will be connected to the output terminal. Okay, so this is my circuit connection. So I can just adjust it to some 10K. Okay, now this biasing values, this has to be minus 12 volts and this has to be plus 12 volts. Okay, once after fine tuning this circuit, I can just click on simulation. So before which I'll see to that the frequency of my signal is 1K initially. I'll show you the operation of the circuit, and let this be equal to 1 volts peak. Okay, and waveform, let it be sinusoid. Okay, so now simulation, I'll double click on this. So as you can see, both my input and output signal is overlapping. So if at all if you want to differentiate between your input and output signal, just you can click on this input channel and click on this properties and change the net color. So instead of the red color, I'll just say blue. I'll say apply. Okay, so you'll get input and output in two different colors, so that you can easily match up, saying that your blue color is your input and red color is your output. But you can see here, since it's a voltage follower circuit, your input and output, they are in phase. Okay, so now what is that you people need to understand over here is, since it's a band stop filter, so which I have designed it at 60 Hertz. So if I just go on reducing this frequency, let me say up to 100 Hertz. Okay, 100 Hertz. So let me select this be in terms of Hertz. Okay, now what is that you're able to see over here is that if I make this time per division less, okay, sorry, if I increase this, so you're able to see that your output is almost decaying. Okay, now I'll reduce it to some 70 Hertz, or let me say 80 Hertz first. So I can see that frequency is almost decaying. Now if I go to some 60 Hertz kind of a frequency, so what that I can witness is that the output is not visible onto my oscilloscope, simply indicating a 60 Hertz signal is not being allowed. So your input signal, which is blue color, it's 60 Hertz signal that is not being propagated to the output terminal. It has been attenuated. Okay, it has been attenuated. The moment this signal becomes, say, around some 70 Hertz or 80 Hertz, then again you will get your input signal back. Okay, now if I increase this to some 150 Hertz, so you can see that your signal is seen onto the output channel. Okay, this is what you people need to understand in case of this band stop filter. However, even we have to perform an AC analysis, okay, to get the response curve. So I'll just stop the simulation, click on simulate. Okay, then go to analysis, AC analysis, and I need to select the terminals, before which I need to connect the connectors onto my canvas. So I'll just go to place, go to connectors, a global connector. Okay, and I'll say this as out. Okay, I'll connect this to the output terminal. I'll go to place, connectors, a global connector. I'll just place it onto my input. Okay, so this is the input probe itself, not a problem. So I say it is in. Okay, so this is my input terminal. Okay, so now I can go to simulate. Okay, then I can go to analysis. In that AC analysis, so start frequency is 1 Hertz, stop frequency I'll limit it to 3 megahertz. Okay, sweep type, let it be decayed, number of points increase it to 100, vertical scale it has to be decibels. Click on output, design your equation, that is V out divided by V in. So to that, click on add expression. So variables are available here. So V out double click on that variable, divided by Vin, that gives you the gain of the circuit. Say OK. So your equation is available here now, and just click on simulate. So you can get the frequency response as desired. So just to make it properly visible, I'll just reverse it so you can see the response properly. So I can add grid to this, both my magnitude response as well as a phase response. So you can see here at 60 Hertz the signal is completely zero, indicating the 60 Hertz signals will be attenuated, and other than the 60 Hertz are slightly attenuated, but in a band of 40 to 100 I can say that the signals will be retained. Okay, signals will be retained, but at 60 Hertz you can see a drastic change, indicating that 60 Hertz signals will not be allowed to move from input to output. So this is how my band stop, specifically a narrow band stop, is going to operate. Okay, thank you.